My name is Beomki from UC Berkeley, and the talk is about the HTS GPU track reconstruction demonstrator for high energy based experiment. So let me just introduce a common tracking software, which is the modern open source HEP tracking toolkit, which is based on the C++ setting, and it also has experiment independent design, as you can see here. There is the detector for Atlas ITK, and Spanix, and the first experiment, and also the ADMX, which was just introduced in previous talk. And it has been serving as a very nice R&D platform to explore new techniques such as GPU parallelization and also machine learning, which we are going to hear in this connecting the dots. And there are some related talks here as well for the backpower library and also for the hyperparameter optimization for HTS software framework. And so let me briefly introduce the history of the HTS GPU studies. So it has been a while since we started the study on the GPU. So there have been a couple of pilot studies, especially for the GPU seeding and also the track fitting with the command filtering. And on the left side, you can see the actual CUDA seeding implemented inside the HTS, and also it's the speed of plot. And there is also the published literature for the GPU-based command filtering, and where we get a very good speed of compared to the multi-threaded CPU. But there is a clear limit when it comes to uploading the full tracking chain based on these studies, because in HTS we have a bunch of the C++ features, but not all of them are supported inside the GPU device, and also the tracking geometry, which has a bunch of one-time polymorphism or the fancy object-oriented programming, is quite problematic inside the GPU device. So as a result, we decided to launch a GPU R&D project to continue early studies and combine them into the single piece. So those are the basic requirements or the main philosophies that we have for our GPU project. So we want to have the same physics performance as the existing CPU algorithms. And we also want to still have the experiment independent design. And we want to have the realistic detector setup, such as realistic tracking geometry, and also realistic inhomogeneous multi-field. And we want to have a perfectly shared event data model, shared by CPU and GPU device. And we want to have support for the single and low precision, and maybe possibly for the half precision, but it has not been discussed yet. And for now, we are primarily focusing on the CPU and CUDA and SQL implementations. The reason for having the CUDA is simple. CUDA has been a standard GPU API, working with the NVIDIA hardware, and it's the leading GPU API. So that's the reason that we want to have CUDA. And the reason that we want to get Thinker is it's a very nice cross-platform heterogeneous computing API, working with NVIDIA and AMD and Intel hardware. And the AMD or Intel is not supported by the CUDA API, so that's why we have the Thinker. So just to have the better coverage of our project. So this is the ecosystem of the HTS GPU R&D. So we have a bunch of similar projects for other purposes. So the traccc is the downstream project, which is for the GPU track reconstruction demonstrator. So that's the final project that we have for everything. And the DETRAY is the GPU geometry builder. So it provides the tracking geometry description without one-time polymorphism or without any object-oriented programming. And we have Coffee library for compile time vector field processor. So simply it's just for the realistic multi-field inside the GPU device. And we have algebra plugins, which provides the vector matrix algebra for multiple plugins. And finally, we have Bangman, which is for the GPU memory management tool. So it provides some very easy interface for the users, so they can play with the GPU memory and also the data object. So let me talk about the Bangman library a little bit here. So how the Bangman work is that they make use of the SDPMR memory resource, which is from the C++17, and they can be used to customize the memory allocation of the STD vector that we are very familiar with. So you can just like customize the memory allocation scheme for the CPU, which is the original one, and we can also customize it for the CUDA seeker and also HEP API. And so in this plot, the left one is what we are using. It's just like a core the SD vector, and then the malloc and the free cores for the constructor and deconstructor respectively. That's what we use in our usual C++ code. And if we use the like upstream memory resource, which is for the PMI memory resource, we can just like customize it for the CUDA seeker and HIP, and we can also put the downstream memory resource, which is for the caching allocator, and this is like just for the reusing the memory allocated reusing the memory allocated in the previous event, so we don't have to waste our time to allocate the memory for every event. So this is just for optimizing our pipeline for when we run the tracking construction for many events. And this compositionality for the memory allocation is used for the in traccc and that way. In traccc, we use it for the metadata model container, and in that way, we use it for as like a container for detector components. And now it's for the vector and matrix algebras inside the algebra plugins that we have. And so as I mentioned before, these algebra plugins provides the vector and matrix algebras required for the track reconstruction. And here in this plugin, users can configure several things at compile time. So one is they can choose if they are going to use the single or double precision. And also they can choose which backends they are going to use. So the backends that we are providing is the CMAS, which is the homebrew algorithm, and also the Eisen and asymmetrics from the root library. The reason that we have like the homebrew CMAS library is that we really need some like the robust plugins which works for CPU, CUDA, and seeker at the same time. Because Eisen is supposed to work for all those backends, but it has not been tested very well, so that's why we have this one for now. And if you see the code snippet here, users can like define the matrix operator object by just like giving the float or double inside the template parameter, and also they can pick up the namespace for the specific backend, and we can just use it for like the Eisen style operations here. And now here is the track construction chain in traccc. So we started from the digitized heat data from the HTS simulation. So here comes the data input, and those data input forms the cluster with the connected component labeling algorithms, and the space points created by the clusterization are used for the seeding algorithm, and we look for the triplets as the HTS does, and those triplets found extend here to the full tracks using the combinatorial gamma filtering, and then finally the full tracks are refined using the nominal gamma filtering. And for this CKEF and gamma filtering process, we get the data rate geometry as a tracking geometry input. And so let me talk about the heat clusterization. So basically we have the three sub-algorithms for heat clusterization. So the first one is the most important thing, which is the connected component labeling, where the neighbor pixels form the cluster to get the the one single measurement. So once we get like a bunch of the clusters per event and on the detector module, the clusters are created for are from the measurement, and during the measurement creation, you calculate the weighted average of the cluster cell positions and also covariances. And once you get the local property of the measurement, then their local property are transformed into the global coordinate to get the 3D positions and also covariance. And those space points become the input to the seeding algorithm. And so for the clusterization GPU implementations, the algorithms is divided into the following steps. So at the very beginning, we create the CCL indices, which record which cluster cells belong to, which cells belong to which clusters, and then from these CCL indices, the number of the clusters is counted from this CCL index vector, and we initialize the vector of the clusters with the proper size. And counting, the reason that we have like a counting process is that we doesn't know how many clusters that we have, so we want to know the size of the detector vector size that we need. And because the GPU does not allow the dynamic allocations inside the device kernels. And so once we have the enough size of the vector, the vector of the clusters is filled with the cells by looking up the CCL indices again. And then we create the measurement by evaluating the local position and variance. And also we get the space points from the measurement by just doing the local to global transformation. And they are very straightforward because the measurement creation or the space point formation are just like one-to-one correspondence. So we don't need any like the vector size estimation. And the blue plot is showing the CPU speed per event and also the secret speed. And we still don't have the implementation yet, but the first implementation speed is not bad, but we are working hard to make it better. And now is the seeding algorithms. And once we get the space points from the clusterization algorithm, the space points are grouped based on the azimuth angle and also based on the longitudinal position, as you can see in this figure. And for every the space points inside the current beam, we find the doublets by iterating the space points in the neighborhood beams. So once if we are investigating one space point here, then we look for all the space points in neighbor beams to find the proper doublets. And once we have all the doublets, and then we try to find the triplets, which is the combination of the two doublets, and they need to satisfy a certain physical criteria such as parameters, curvatures, etc. And once we have those triplets with the good physical property, we try to find the local properties of the space point. Again, so we just run the globe to local transformation to get the measurement at the surface of the bottom space point, and they become the input to the trafficking or combinatorial combinatorial. So the GPU implementation is quite similar to the clusterization part in terms of the counting. So as for the clusterization algorithms, we need to know the size of the doublet or the triplet containers before we actually filling those containers. And so all the like sub algorithms of the triplet finding, such as the doublet finding or triplet finding, are divided into the counting and finding process. So during the counting, we count the number of the objects, such as we count the number of the doublets or triplets. And then once we count the number of the objects, we initialize the vector containers with the proper size. And once we have the vector, we populate the object into the vector containers. And once we do that for the triplets, and we just run the parameter estimation, which is quite straightforward because it's just like a one-to-one correspondence. And so this is the performance plot, and this white figure is showing the very preliminary the seeding efficiency from the seeding algorithms. And the speed itself, it's not so bad compared to the single core CPU. It's about like a 10 for the 200 pilot events in track element detector. And in the case of Secret, it's slightly faster than CUDA because we already have the clusterization algorithm for Secret, which means that the space point container is already located inside the GPU device, so there is no like the data transfer between the host and GPU device. That's why Secret is slightly faster than the CUDA algorithm here. But in the end, once we have the clusterization algorithm for CUDA, they will get the same speed. And also inside Dover, it's not as good as the single precision benchmark, but it's quite understandable because the RTX GPU is not supposed to be good for double precision. And so once because for the command filtering or combinatorial command filtering, as I said, we need a tracking geometry input. And what we want to do with the stack tray is that we want to build a tracking geometry without runtime polymorphism. And the reason is that the runtime polymorphism or the object-oriented programming with the pointers, which is very widely used for the detector building, like inside the G24 or T geometry, they are not very GPU friendly. And so in that tray, we want to remove the runtime polymorphism, and we want to determine every detector configurations during the compile time. So during the compile time in that way, we specify the detector configuration with the metadata, and we initialize the proper tuple containers for different types of the components. And so we don't have any like inheritance or polymorphism here. And during the runtime, we just like fill the components inside the tuples. And then we build the detector geometry. And the way to use the detector geometry inside the GPU is quite easy. So the host or device tray of the detector can be determined by the Bangman container type. So if we use the host vector type or the detector, then it becomes the host detector. And if we use the Bangman device vector, then we can use the detector inside the device. So the way to use the device detector is quite simple. We just build the detector in the host side, and we just make the real-time object, which can be passed into the GPU device. And once the real-time object is passed into the GPU device, we can just like build the device detector, as you can see here. In the corner, we just pass the real-time object here, and then the detector is built by putting the data inside the constructor or the device detector. And for the from the detector, we also provide some propagation tools. So we are providing the 3 core classes. The first one is the stepper, which is used for advancing the track state through the tracking geometry, and it has the adaptive Untitled method. And you can see the Georgiana stuff on Thursday for its own benchmarking. And we have Navigator, which provides the next candidate surface for the tracks which just get inside the volume, because the track needs to know which surface it needs to go for every geometry that it passes through. And so it provides the next candidate surface inside the volume, and also its distance to the next surface. And the surface search is based on the ray tracing. And we finally have a propagator, which is steers the workflow between the stepper and navigator. And this slide is showing the propagation speed benchmark. And we are also using the pixel part of the track detector for our benchmark. We have used the 2 Tesla microgrid with the RKN stepper, And for this simple geometry setup, we got a quite good initial benchmark result. For example, for the single precision, we got about like the one order of magnitude speed up for 10,000 tracks. And for the precision, it's not as good as the single precision, but it's still not bad, which is close to one order of the magnitude. And finally, we have another library which is called Coffee, and it has been developed for the magnetic field interpolation, so we can have the inhomogeneous realistic B field for our tracking. And so the actual motivation is for the magnetic field interpolation for realistic magnetic field, but it can be used for any type of the vector field. So it's like developed for the more general purpose right now. And one of the strong features of Coffee is that everything is known at compile time. So the GPU API is known at compile time, and the dimension of the vectors also known at compile time, and the interpolation algorithms that we want to use can be provided at compile time. And so the first benchmark result is quite promising. So when you try to render the autonomous magnetic field at the origin, the lookup time for the 1 million pixels is quite promising. So for example, for CPU, it takes about more than about 200,000 milliseconds. But for the GPU, it takes about only 90 milliseconds for nominal CUDA. But with the texture memory, it gets much better with the 17 milliseconds. So it's quite promising. And so this is we still don't have any stuff for the Kalman filtering yet, but we definitely have a good plan for the Kalman filtering implementation. So one expected difficulty with the Kalman filtering or combinatorial Kalman filtering is that the branching divergence. So it's from the nature of the symmetry architecture. So because in the symmetry architecture, all threads inside the block, yeah, I'm almost done. In symmetry architecture, the threads always need to execute the same instruction. So for example, they cannot run the different operations at the same time, which means that if you see the left figure here, if you, let's say, just like the implemented Kalman filter inside the CUDA very nicely. So for example, the thread 1 is running the propagation and Kalman filtering for the first track, and the second thread do the same thing for the second track. We go on, and let's say the first thread came across the surface earlier than the other thread, and they will try to run the Kalman filtering inside the surface, which means that any other thread will get either because it needs to run the Kalman filtering, and they don't need to run the Kalman filtering because they haven't met any surface yet. So this branching divergence can be very problematic when we optimize the Kalman filtering performance inside the GPU. So our current idea is that doing some clever thread synchronization to run the Kalman filter simultaneously for all thread. So basically, all the thread wait for any other thread come across the surfaces, and then once every thread come across surface, then we run the Kalman filtering at the same time. That's what we are thinking for the Kalman filtering optimization, but we might need some time to implement this in the prototype. So this is the summary. The HTS R&D project are being developed to offload the traction algorithms to the GPUs, and BangMem is the core library for defining the detector geometry, and also the event data model shared by CPU and GPU. And algebra plugins provides the useful vector and matrix algebra for that array and traccc. And that array construct the tracking geometry for Kalman filtering, and so without any runtime polymorphism. And the current benchmark study on propagation inside the tracking detector is promising. And we have recently launched a copy library, and it is used to incorporate inhomogeneous magnetic field in GPU devices. And finally, traccc is the downstream project for GPU track demonstration. And we currently have demonstrated clusterization and seeding algorithms in CUDA and Seeker, but there are still many works needs to be done to get the final event throughput. For example, we need a greater implementation using the battery tracking geometry. And we also need to utilize the backend downstream memory resource to reuse the previously allocated memory, which means that we still need to optimize the overall pipeline for like many events, which we have not done yet. And also we need to do the multi-threading benchmark for apple-to-apple comparison between the CPU and GPU. Okay.
Thanks very much for this nice summary of all the interesting developments which are ongoing in this area. Questions? Follow was first, I think. He was a millisecond faster than you.
Hi.
I had a question about this. You build the library, the geometry, basically a compile time. Does this mean that every version of the geometry is a separate library that you load like a plugin and you say, okay, this is the version of 2026, this is the version of 2027A, 2027B? How would you handle the evolution? From 1 year to the next, maybe the number of components of a given type changes.
No, that's okay.
Okay.
That the component can change. When you need to recompile is when you introduce a new shape.
Because for the magnetic field, you said that the size of the arrays was fixed. Okay.
Yeah, but I think
so if you wanted, for instance, to describe a detector that has a new shape in it, you need to recompile for your application. But once you have this shape, because the polymorphism was the problem of the initial common filter paper.
But you see what I'm thinking is that if you need a new geometry for one reason or another compiled, you need a new library. So you need a mechanism to load the different versions of this library.
Maybe we can have like a multiple metadata for the same data, I think. So that's also possible, I think.
Or you can have multiple versions in the same library.
Yeah. I think that's not impossible. Yeah.
All right. I'll ask you another question offline because it's going to take time and I'm sure it's
Yeah, so can you go to the timing slide where you claim SYCL is faster than CUDA?
No.
Yeah, so out here you're saying that SYCL is faster because the space point medium is already in the GPU device, right? Can you do a test like that for CUDA where something like essentially an apples to apples comparison where this whatever is required is already in the GPU, and then you run the CUDA library?
I mean, can you repeat the question?
So essentially what you're saying here is that you made SYCL faster than CUDA because you threw stuff into the GPU already.
Okay, yeah. So if we remove this like a space point DDM located inside the GPU for the Seeker, then still Seeker a little bit faster. I mean, if we make every condition the same.
I mean, that's how you should measure timing at the end of the day, right? You're checking how good the computation, how good the library is in optimizing stuff. And naively, I would think that CUDA being proprietary would be the fastest.
No, actually not. I mean, we have observed this in the other studies that the Seeker with the CUDA backend. So basically, it's a Seeker, but its backend is the CUDA still. So basically, they are same thing. And one different thing is that this CUDA is compiled by MVCC compiler.
Yeah.
And this Seeker with CUDA backend is compiled by the Clang compiler.
Oh,
and the Clang compiler looks a little bit faster than this CUDA version. And we don't know it's from the like host part or it's from the device part of the algorithms. But
no, if you're entering compiler territory, yes, I can understand one being faster than the other.
The Clang, that's what I said before. The Clang compilation of CUDA seems to consistently be faster.
Yeah,
There
we
must
have.
be a better optimization. Torchana should be
Yeah.
we are directed to
Yeah,
Torchana
this is
tomorrow.
something that we didn't know. I mean, we were still using LPCC, so.
We just stumbled upon it, and Torchana did a study about it. It's consistent.
Okay.
Yeah, actually,
In
we
that
didn't
case, then
find
we should
them.
also try for our stuff.